Hello, मेरे future doctors and engineers. Welcome, welcome, welcome. आज हम chemistry का a very important chapter, probably the most important chapter, chemical bonding को master करने वाले हैं. Seriously, चाहे आप NEET की तैयारी कर रहे हो या JEE की, इस chapter से questions आने ही आने हैं. So get your notes ready and let's just dive right in. So let's start with the most basic question of all. आखिर ये atoms आपस में जुड़ते ही क्यों हैं? I mean, why can't they just exist alone? The answer in one word is stability. देखो, नेचर का एक फंडामेंटल रूल है, हर चीज, हर सिस्टम मोर स्टेबल होना चाहता है, अपनी एनर्जी को कम करना चाहता है. एंड बॉन्डिंग इज जस्ट नेचर्स वे फॉर एटम्स टू अचीव दैट स्टेबिलिटी. Okay, so here's our game plan for today. We'll start with the basic funda of bonding, then figure out the 3D shapes of molecules with VSEPR. उसके बाद, we'll see the magic of hybridization with VBT and then jump into the more advanced molecular orbital theory. We'll also cover a special case, hydrogen bonding, and finally, we'll wrap it all up with a quick revision checklist for your exams. Ready? चलो, शुरू करते हैं. All right, section 1 it is, bonding का basic funda. यहाँ हम सबसे पहले, सबसे simple model से शुरुआत करेंगे, a model given by Kossel and Lewis. You can say that this model is the very foundation of chemical bonding.
So, the first rule of the bonding game is the octet rule. It's pretty simple, really. ये rule कहता है कि atoms will do anything. They'll gain, lose, or share electrons just so they can have 8 electrons in their outermost shell, their valence shell. Why 8? Because that's the configuration of the noble gases. And we all know noble gases are super stable, right? It's all about achieving that stable configuration.
So the question is, how do these atoms complete their octet? Well, there are two main ways to do it. One involves a complete transfer of electrons, and the other is all about sharing. Chaliye, let's understand both of these in detail.
To understand an ionic bond, let's take a real-life example, our very own common salt, namak, or NaCl. Here, sodium is a metal, right? So it just permanently gives away its one valence electron to chlorine. Now, by giving up an electron, sodium becomes a positive ion, a cation. And chlorine, by taking that electron, becomes a negative ion, an anion. A positive or negative charge ke beech, there's a very strong electrostatic force of attraction. And that, my friends, is what we call an ionic bond. Simple as that.
Now let's talk about the covalent bond. You can call this the sharing is caring bond. It's just like when friends share their tiffin box in school. Here, atoms share their electrons. For example, take 2 chlorine atoms. Each one needs one more electron to complete its octet. So what do? They each share one electron with the other, forming a single bond. If 2 pairs are shared, you get a double bond, like in an oxygen molecule, O2. And if 3 pairs are shared, you get a triple bond, like in a nitrogen molecule, N2. By sharing, everyone's happy.
So, it all seems pretty straightforward so far, right? Just get to 8 electrons and you're stable. But wait, chemistry is never that simple. The octet rule is a great starting point, but it's not universal. Just like any rule, it has its exceptions. So, chaliye dekhte hain, where does this rule fail?
Okay, pay close attention now, because this section is a huge favorite for exams. The first exception, the incomplete octet. In some molecules, the central atom has less than 8 electrons. For example, in BF3, boron only has 6 valence electrons, and in BeH2, beryllium only has 4. And yet, these molecules exist, and they are stable.
The second case is the expanded octet. Here, the central atom has more than 8 electrons. Like in PCl5, phosphorus has 10 valence electrons, and in SF6, sulfur has 12. Now you might be thinking, how is that even possible? Well, the reason is the presence of empty d orbitals. This is only possible for elements in the third period of the periodic table or beyond, because they have these vacant d orbitals that they can use for bonding.
And the third exception, odd electron molecules. In these molecules, the sum total of all valence electrons is an odd number, like in nitric oxide, NO. Now think about it. If the total number of electrons is odd, it's just impossible for every atom to have a complete octet, right? So the crucial takeaway is that the octet rule fails in all 3 of these cases.
Okay, so far, all the Lewis structures we've drawn have been 2D, totally flat. But in reality, molecules are 3D objects. They have a specific shape. So how is this 3D shape determined? The answer lies in our next theory, which is super important for your exams, VSEPR theory.
VSEPR stands for Valence Shell Electron Pair Repulsion Theory, and the core idea is hidden right there in its name. It says that the electron pairs in the valence shell of an atom, whether they are bonding pairs or non-bonding lone pairs, they repel each other. Why? Because they all have a negative charge. So to minimize this repulsion, these electron pairs try to get as far away from each other as possible in 3D space, and that arrangement is what determines the molecule's final shape.
Now, not all repulsions are created equal. Pay attention to this slide. This is the most important concept in VSEPR. The strongest repulsion is between two lone pairs, LP-LP. A little weaker than that is the repulsion between a lone pair and a bond pair, LP-BP. And the weakest repulsion of all is between two bond pairs, BP-BP. Why, you ask? Because a lone pair is only influenced by one nucleus, so it spreads out more. It's more bulky. Remembering this order is absolutely crucial for your exams.
Chetty, let's look at a few examples. First, let's take the ideal case where the central atom has no lone pairs, only bond pairs. Look at this table. If there are two electron pairs, the geometry will be linear, like in BeCl2. 3 pairs, trigonal planar, like BF3. 4 gives you tetrahedral, like CH4. 5 is trigonal bipyramidal, and 6 is octahedral. These are the perfect ideal geometries.
But the real fun begins when lone pairs enter the picture. Let's see how lone pairs completely change the game. Methane, CH4, has 4 bond pairs and 0 lone pairs. It's a perfect tetrahedral shape with a bond angle of 109.5 degrees. Now, look at ammonia, NH3. It has 3 bond pairs and 1 lone pair. This lone pair repels the bond pairs more strongly, pushing them down, so the shape becomes pyramidal, and the angle shrinks to 107 degrees. In water, H2O, it's even more extreme with 2 bond pairs and 2 lone pairs. Here, the LP repulsion is the strongest, squishing the bond angle even more. The shape becomes bent or V-shaped, and the angle is just 104.5 degrees. This clearly shows just how powerful that lone pair repulsion is.
So, VSEPR predicted the shape, but it didn't tell us why. Why do atoms form these very specific angles, like 109.5 degrees? VSEPR doesn't have an answer for that. To find out, we have to go one level deeper and look at how the orbitals themselves combine. Chelyeb hybridization, which is part of the Valence Bond Theory.
So what exactly is hybridization? Well, you can think of it as a remix of atomic orbitals. In this process, orbitals from the same atom that have slightly different energies, like 1s and 3p orbitals, they mix together. And this mixing creates a brand new set of orbitals that are all identical in shape and energy. We call these hybrid orbitals. And these new hybrid orbitals are way more effective for bonding than the old pure orbitals were.
Now for the part you've all been waiting for, a shortcut trick. To find the hybridization of the central atom in any molecule, all you need to do is calculate its hybridization number, or H. The formula is super simple. It's just the number of sigma bonds plus the number of lone pairs on that central atom. If H is 2, the hybridization is sp. If it's 3, it's sp squared. 4 is sp3, 5 is sp3d, and 6 is sp3d2. Make sure you write this table down in your short notes. It's going to be a lifesaver.
Chelye, let's understand this process using methane, CH4, as our example. In its ground state, carbon's configuration is 2s squared 2p squared. It only has 2 unpaired electrons. So how can it form 4 bonds? Well, first, one of the 2s electrons gets promoted to the 2p orbital. Now, in this excited state, it has 4 unpaired electrons. Then, this 1s and 3p orbitals mix together to form 4 brand new, identical sp3 hybrid orbitals. These 4 orbitals point towards the corners of a tetrahedron, and they each overlap with the 1s orbital of a hydrogen atom to form 4 CH sigma bonds. And that is why methane has a tetrahedral shape.
And here's a really interesting point. Both nitrogen in ammonia and oxygen in water are sp3 hybridized. If you use the shortcut formula, you'll see the H number is 4 for both. But their shapes are different. Why? Because in ammonia, out of the 4 sp3 orbitals, 3 form bonds and 1 holds a lone pair, giving it a pyramidal shape. And in water, out of the 4 sp3 orbitals, 2 form bonds and 2 hold lone pairs, giving it a bent shape. So same hybridization, but a completely different story when it comes to shape.
Elements from the 3rd period onwards can also use their d orbitals. In PCl5, phosphorus is sp3d hybridized. Its shape is trigonal bipyramidal. And here's a very important exam point. In this shape, not all bonds are equal. The 3 bonds in the plane are called equatorial, and the ones above and below are called axial. These axial bonds experience more repulsion, so they are slightly longer and weaker. On the other hand, in SF6, sulfur is sp3d2 hybridized. The shape is octahedral, and here all 6 bonds are absolutely identical.
So VSEPR told us the shape, and VBT explained why we get that shape. But even VBT isn't perfect. There's a very simple molecule whose magnetic behavior VBT just cannot explain. Chaliye dekhte hain, what is that puzzle?
So here's the puzzle for VBT. If you draw the Lewis structure for oxygen, O2, you'll get an O double bond O, where all the electrons appear to be paired up. According to this, oxygen should be diamagnetic, meaning it should be repelled by a magnetic field. But experiments show that liquid oxygen is actually paramagnetic. It's attracted to a magnet. Why? VBT has no answer for this. And to solve this puzzle, we need our final and most advanced theory, molecular orbital theory.
So what's the main difference between VBT and MOT? VBT assumes that electrons are localized or fixed in a bond between 2 specific atoms. Atomic orbitals just overlap. MOT, on the other hand, has a totally different approach. It says that when atoms combine to form a molecule, their atomic orbitals also combine to form brand new orbitals that belong to the entire molecule. We call these molecular orbitals. And the electrons are delocalized in these MOs, meaning they move freely across the whole molecule.
So, how are these molecular orbitals formed? The principle is called the linear combination of atomic orbitals, or LCAO. When 2 atomic orbitals combine, they form 2 new molecular orbitals. One is the bonding molecular orbital, or BMO. It's formed by constructive interference, has lower energy, and it stabilizes the molecule. The other is the anti-bonding molecular orbital, or ABMO. It's formed by destructive interference, has higher energy, and it actually destabilizes the molecule.
Okay, everyone, I need your full attention here. This is a common mistake alert. When we fill electrons into these molecular orbitals, there's a small twist that trips up a lot of students. For diatomic molecules up to nitrogen, so boron, carbon, and nitrogen, the pi2p orbitals have lower energy than the sigma 2p orbital. But for oxygen and fluorine, the order flips. The sigma 2p orbital becomes lower in energy than the pi2p orbitals. This happens because of something called sp mixing. This difference is a very common question in exams. So, let's use MOT to finally solve the oxygen case. An oxygen molecule has a total of 16 electrons. When we start filling them into the MO energy diagram, starting from the lowest energy level, they fill up one by one. Now, when we get to the last 2 electrons, according to Hund's rule, they will go into the 2 separate anti-bonding pi star orbitals. That's pi star 2px and pi star 2py, 1 electron in each, and they will be unpaired. And it is these 2 unpaired electrons that make the oxygen molecule paramagnetic. Aha! Puzzle solved.
MOT gives us another really powerful tool, and that's bond order. The formula is really simple. It's just half of the number of electrons in bonding orbitals minus the number of electrons in antibonding orbitals. This number basically tells us how many bonds exist between 2 atoms. Is it a single, double, or triple bond?
Let's apply this formula. For nitrogen, N2, there are 10 bonding and 4 antibonding electrons. The bond order comes out to be 3, which means a triple bond. Perfect. For oxygen, O2, there are 10 bonding and 6 antibonding electrons. The bond order is 2, a double bond. Correct. And for helium, He2, there are 2 bonding and 2 antibonding electrons. The bond order is 0. This means the He2 molecule simply does not exist. So you see, MOT not only tells us the bond type, but it can also predict if a molecule will be stable or not.
So we've talked about strong bonds like ionic and covalent bonds. Now let's talk about a special, somewhat weaker, but incredibly important attractive force, and that is hydrogen bonding.
A hydrogen bond forms when a hydrogen atom is attached to a very highly electronegative atom, specifically fluorine, oxygen, or nitrogen. Just remember, Fon. Because of the large electronegativity difference, the hydrogen gets a partial positive charge, and the FO or N gets a partial negative charge. Now, this partially positive hydrogen is attracted to the negative FO or N of a nearby molecule. That attraction is the H-bond. It can be intermolecular between different molecules, like in water, or it can be intramolecular within the same molecule, like in O-nitrophenol. You know, the unique properties of water, like its high boiling point, are all because of this extensive hydrogen bonding.
Phew! We've covered a lot of ground. Now it's time to bring everything together and revise all the important points before your exam. Chaliye, let's do a rapid-fire revision of this chapter.
Take a look at this master's summary table.
The Kossel-Lewis theory explains why bonds form, because of the octet rule. VSEPR explains the shape of molecules, based on electron pair repulsion. VBT explains how those shapes are formed, through hybridization and overlap. And finally, MOT explains properties like magnetic nature and bond order, using the concept of molecular orbitals. And here they are, the top 5 takeaways from this chapter that you absolutely must remember for your exam. 1. Bonding happens for stability. 2. Lone pairs repel more than bond pairs. 3. The shortcut for finding hybridization. 4. The non-equivalent bonds in PCl5. And 5. MOT is the reason we know why O2 is paramagnetic. Don't forget to revise these points one last time.
All right, let's end this discussion with a thought-provoking question for you. If mixing atomic orbitals, or hybridizing, creates more stable bonds, then why don't all orbitals in all atoms just hybridize all the time? Think about it. The hint lies in the concept of energy. Every process has an energy cost and an energy benefit.
So I really hope this masterclass has made every concept of chemical bonding crystal clear for you. अगर आपको ये सेशन पसंद आया तो please hit the like button, share it with all your NEET and JEE friends, and don't forget to subscribe bell for more helpful content like this. Keep learning and keep growing. All the very best.